Hello students. In this lecture I will be discussing with you about channel length modulation of MOSFET. It is a phenomena, it is in short it is called CLM. It is such a phenomena which is a similar phenomena is being observed as early effect you have studied in the BJT. It is something like that that is seen in MOSFET channel length modulation. Let us first refer to this figure of N-channel enhancement type MOSFET we are considering, and you know that in such a MOSFET, two N heavily doped regions N plus and N plus are termed as source and drain terminals, and between them the channel is formed, and this dotted portion is the oxide layer, and above that the metallization is done and the gate terminal is formed, and at the gate terminal a voltage is being applied as VGS1 of value VGS1, which is greater than the threshold voltage of the MOSFET, and this VGS1 is the voltage between gate to source. The length of the channel is specifically denoted by L, capital L. So this channel length is important parameter to explain this phenomena. Now let us refer to this characteristic curve. You know the VI characteristic curve is plotted between VDS and ID for our N-channel enhancement type MOSFET is divided in two regions primarily. One is ohmic region, inside which this VDS and ID variation will be linear, and the characteristic curve will be almost linear and flat. If we do piecewise linear approximation, that means if we segregate this region of curve into small pieces, we will be we can approximate that portion of the curve like a straight line, or we can compare it with a straight line, although it is a curve. So that's why this will be called ohmic region or linear region, and within this region the properties of linearities will hold, and the MOSFET will be, you know, behaving like a resistor. And after this voltage is achieved or applied between drain to source terminal, which is called pinch off voltage, here it is written as VGS1 minus VTH. This is nothing but the pinch off voltage VP you have seen. So once this pinch off voltage is attained by between drain to source terminal by the MOSFET, we can observe that the current will be becomes constant, and thereafter it will no more increase, and that region of operation is generally called saturation region, or sometimes it is also called active region of operation, and during that operation VGS is equal to VGS1, the applied value. So this is the VI characteristics. Now let us move on to understand the phenomena of channel length modulation. So let us see one important thing, that once this majority carriers in terms of electrons for this MOSFET, because it is, we have selected N-type enhancement, N-channel enhancement MOSFET, so majority carriers are electrons and they will be passing from source to drain terminal. So within this region of within this ohmic region of operation, when initially the VDS is at small value, that means from 0 to this VP, within this region when the value of VDS lies, the MOSFET will be behaving like a resistor, and the VI characteristics will be confined to the ohmic region or linear region. That means in linear region or in the ohmic region, it is of such a value VDS that MOSFET will be behaving like a resistor. And you know that in a resistor, when a current is flown through a resistor, voltage drop or potential drop is appeared across it. So this channel will be behaving like a resistor when the value of VDS lies between 0 to VP, and during that time, as more and more the carriers in terms of electrons are passing from source to drain, since this channel will be, or the device will be acting like a resistor, it will be introducing potential drop across the drain to source terminal, because this channel is shorting or connecting the drain to source terminal. So more and more electrons are passing through this channel from source to drain, more and more potential drop will be developed across this channel, and that is to be added with the voltage between drain to source terminals. That means that will be added to the VDS value, VDS voltage. And if that is happening, so you can see from here that it is a p-type substrate and the channel is n-type, so between them a depletion layer will be formed. So more and more additional potential drop due to the passage of electron from source to drain, that potential drop will be added to the voltage between drain and source, that means VDH. And if that is being added, it will mean that the width of the depletion layer between the substrate and the channel will be more towards the drain end than near the source end, and as a result of that, it will mean that the channel width will be less towards the drain end than towards the source end. That means, what I mean, that refer to figure number 2. So more and more electrons are moving from source to drain, more and more potential drop will be appearing across the channel, and that potential drop or the voltage will be added to the voltage applied between drain to source, and so that will increase the depletion layer. Suppose in this case the width of the depletion layer was something like this. It is uniform between p-type substrate and n-type channel between them. This is p-type substrate and this is n-type channel. So suppose this was the initial depletion layer, but once the carrier movement is happening because of this drain to source voltage or this external voltage, small external voltage applied as plus VDD, positive voltage at drain terminal, this is the drain terminal, then these electrons will be starting to flow at heavy numbers between this source to drain, and that will, as more and more they are moving through this channel, more and more potential drop will be appearing, and that will be adding up to this external VDD plus VDD, and that means the width of the depletion layer between substrate and the channel will be more towards the drain side. So you can see from here that initially the width of the depletion layer was something like this between the substrate and the channel. Now it will be something like this. So you can see initially it was uniform horizontal. Now the width of the depletion layer at this region near the source is far less than the near the drain. So in this area the width of the depletion layer is far more than this source area. So what does it mean? The width of the depletion layer is pushing the channel width to a reduced value. So what does it mean? The channel width, as a result of increase of depletion layer width, the channel width is reduced. So now refer to the figure 3. If furthermore, if this is the region of operation here, based on figure 1, this is the region of operation, because here it is almost a straight line, it is uniform, it is behaving like a resistor, so it is a straight line. So for figure 2, the characteristics will be something at here, and for figure 3 the characteristics will be something at here. It is almost equal, touching the applied voltage, that is VP, which is the pinch off voltage. So at this point of 3, this VDS is something like VP, or attain the pinch off voltage. So at the pinch off voltage, what does it mean? The channel will be reduced in the channel width will be reduced at a such value that there will be no chance of further movement of electrons through the channel from source to drain. So with reference to the figure 3, we can say that the channel is completely pinched off and no further electrons will move from source to drain. So at this point, at this particular point, because of VDS equal to VP, the pinch off voltage is achieved across the drain to source terminal. So it will make the width of the channel, it will make the depletion layer width at a such high value that will in turn reduce the channel width to a very low value, almost negligible, and that negligible channel width will not allow any further flow of electron between the source and drain terminals ideally. So what does it mean? after this voltage is achieved, if we further go on increase the voltage of VDS, we should be getting a flat current, flat VI characteristics. That means the VI characteristics will be parallel to the voltage axis. So this is the constant current region. Now, in this case, we have not mentioned anything about channel length modulation or CLM. So this is all this happening without the application or without the application of the idea of CLM. So now let us apply the idea of CLM on this. Suppose after this VDS is equal to VP point is achieved, that means this point number 3, the stage number 3 is achieved, and after that we are considering the VI characteristic as constant. So in reality this characteristic will not be constant, but it will go slightly higher up. That means in fact in reality we can see with the help of this phenomena CLM that current will not be constant, but drain current will still increase a little bit. Okay, and this curve will not be flat to this parallel to voltage axis, but it will go upward, this curve. Now let us see how this can be explained. So when at this point VGS1 equal to VTH equal to VP, VGS1 minus VTH equal to VP is achieved or given to be between the drain to source terminal, if after that this applied voltage between drain to source is little bit increased and the point is selected, this point is selected over this, that means the applied voltage, this is now is my applied voltage, and this additional voltage is marked as V, delta V, if this is my applied voltage. So what is VDS now? VGS1 minus VP plus delta V. So this is the additional voltage I have applied between drain to source terminal. So as a result of that, we know the relation between electric field is nothing but it is voltage divided by the distance between the 2 points within which the voltage is being applied. So the 2 points are the 2 terminals, source and drain. So between them the electric field will be created, and this additional voltage will be added to this existing voltage VGS1 minus VP, and that will increase the electric field between the source and drain terminals. And what does it mean? This additional electric field will be forcing the electrons more towards the drain end than towards the source end. So the electrons will feel a greater force because of this additional electric field that is being generated because of this additional application of delta V voltage. Now, so this within this channel, this whole voltage is appearing. So that means the electric field is between these 2 terminals, source and drain, and therefore it is, since it is proportional to delta V, so we can say that this electric field is nothing but proportional to this voltage VGS1 minus VP minus delta V. But initially when this delta V was not there, it is just proportional to VGS1 minus VP. But now since we have applied extra voltage plus delta V, so this channel or this L length of channel is absolutely responsible for this total voltage VGS1 minus VP plus delta V, and this length will be proportional to this voltage, and this voltage will be proportional to the electric field. So on the contrary, we can say that the electric field between source and drain terminal will be proportional to this total voltage VGS1 minus VP plus delta V, and this voltage will be proportional to be applied for length L of the channel. Now initially when this delta V was not there, VGS1 was minus VP will be proportional to the length, but now this additional voltage is proportional to this length. So what does it mean? It means that actually the previous VGS1 minus VP voltage is not exactly lying at this point, because now at this point is up to this point, from source terminal to up to this drain terminal, this whole voltage is proportional. So the original voltage for VGS1 minus VP is something ahead of that last terminal point. It is something ahead, something like here, not like here. So suppose it is corresponding to this region. Previously it was corresponding to this region. Now it has come down to this region. So what does it mean? Previously the applied voltage VGS1 minus VP was proportional to this whole channel length, but now this VGS1 minus VP is proportional to this reduced channel length. Suppose it is denoted by L prime. Okay, I once again repeat, previously this VGS1 minus VP was proportional to this whole channel length L, but now it is proportional to the reduced channel length L prime, because this additional channel length, what is being reduced here, suppose it is denoted by delta L, this much, that is because of this application of delta V. That means this delta V is proportional to delta L, or rather on the contrary we can say delta L is proportional to delta V. That means because of this delta V in this VI characteristics we have shown this value, this will be making the length of the channel to be reduced by an amount delta L. So we can say this L dash is equal to L minus delta L. Okay, so if we now further go on increase this delta V, if it is selected here now, so this much is delta V now, or here this much is delta V. As we go on further increasing the delta V along this voltage axis VDS, the channel will be, the length of the channel will be this point up to this drain terminal will be moving towards the source terminal more and more. So as a result of that, the length of the channel will be further reduced and reduced and reduced. Okay, so L prime will be far more shorter than L. And so from this relation E equal to V by D, we can say if V is increased, as we are showing here that V is increased, electric field is increasing, or as a or at the same time this L is decreased. So this D is nothing but L. So this L is now becoming L prime. In some, if it is further decreased, suppose that is L double prime, L triple prime and something. So if it is decreased, denominator is decreased means electric field is increased. Numerator is increased means electric field is increased. So what does it mean? As more and more channel length is being decreased, so the pinch off is actually happening in this case when the channel length is decreased to L prime. The pinch off is happening not at this point of drain terminal, but much more earlier at this point. That's why I have at the beginning told you this is something like the early effect as it is observed in a BJT. So here this point of pinching off by the of the channel observed in this MOSFET will be coming or moving towards the source terminal, and it is making the pinching off of the channel is happening earlier than the previous case, as more and more voltage is being applied between drain and source terminal. So here in this case, the as VDS is increased along this in terms of delta V along this voltage axis towards the right, more and more the channel will become, the length of the channel will become shorter, and this point of pinch off, initially it was here and now it will be moving towards the source terminal. So as a result, the pinching will be of the device, pinch off of the device will be happening at a earlier time. That means at a reduced length of the channel. So if we now again reduce the delta V value, that means if we now come back to a lesser value of VDS, or moving towards the pinch off voltage point, or moving towards the left side along this voltage axis, what we will be seeing? We will be seeing that the length of the channel without decreasing, it will now increase further. So as voltage is increased, the channel length will be decreased and the pinch off will be happening earlier. that means this pinch off point we will be moving towards this left. Or if we decrease the voltage delta V along this VDS axis, that this pinching off of the channel will be occurring later or late, and the length of the channel or the pinching point of the channel will be more towards the drain side, or the length of the channel will be increased. So we can say here that this length of channel L is proportional to delta V. So the channel length or the variation of length of the channel is dependent on the variation of delta V, and delta V is the variation of drain to source voltage. So by varying the drain to source voltage, we can vary the length of the channel, and this variation is called modulation, and this phenomena is hence called channel length modulation. And how the channel length modulation is happening? It is due to the variation of drain to source voltage. So now let us see why I have told you that without channel length modulation, we will be considering that this saturation region of operation, the drain current in the saturation region of operation is constant. But in reality, this is not so, because the drain current curve will be moving little bit upward. That means the drain current will be increasing. Now with so this is without channel length modulation, without CLM, and this upward increased curve is with CLM. Now let us see why. Now you can see, since this reduction of channel length or this L, because of the application of del V, that means E, electric field between drain and source terminals, is equal to V by L, and this L is the length of the channel. So if L is reduced, or because of V is increased, that means it is reducing and it is increasing, so electric field is increasing. Now if electric field is increasing, so the electrons which are moving from source to drain will be experiencing or feeling more amount of force because of this field to move from source to drain terminal quickly. So although it is happening that due to the reduced channel length, the pinching off is happening over here rather being happening over there in the previous case, but since it is now happening at earlier time, so from this point it needs to complete its journey up to the drain terminal, because since at this point the pinching off of the channel is now happening and it needs to complete its rest of the journey. That means the length of L minus L prime, this is the length the electrons need to cover, because in the previous case, based on the applied voltage VDS, the pinching was occurring at length L. Now due to the application of plus del V additional voltage, the pinching is occurring of the channel at L prime. So the electrons are short on journey. The electrons still need to move a length L minus L prime, and for movement of this much of length, it needs some extra amount of force, and that force it will be getting from this increase of electric field. So therefore at this point where this pinching off is now happening at earlier time rather from happening at there from the previous time, they will be, because of this increased electric field between source and drain, they will be feeling much more acceleration at this point to complete their rest journey L minus L prime distance. Okay, so with this additional force, additional application of electric field, they will be able to complete the journey of L minus L dashed length through the channel, and they will, with this additional force, they will be easily reaching the drain terminal and complete their journey. And once they are reached at the drain terminal, through the external circuit, the drain current will be increased and drain current will be still allowed to be flown. So as a result of that, we will be seeing with this channel length modulation concept, this drain current, although it is pinch off is happening over at this point number 3, the current is not constant, but still there is scope, since the electrons are completing with the journey because of CLM happening at this point. Electrons will still be able to complete its journey all over, covering this length of the channel from source to drain, and as a result in the external circuit the drain current will be flown, and this current will be increased somewhat than the previous occasion when the channel length modulation was not there, and so that will be reflected in the VI characteristics by this, that the curve in reality after this point VP, that is position number 3, it will not remain flat, but it will go little bit upward than the previous occasion. So actually in reality with the voltage axis, the flow of drain current will not be constant, but it will still increase further. So that means this above curve can be explained with the help of with CLM concept, and the previous concept is based on without CLM. Now let us find out the drain current expression for with CLM and without CLM. So let us first find without CLM ID. ID is drain current. The expression is, you know, mu Cox prime W by L VGS minus VTH whole square divided by 2. Okay, so now what is mu? Mu is the mobility of the carrier. In this case it is mobility of the electrons because it is n-type in channel enhancement MOSFET. So this is mobility in this case is of n-type. So we can say also this is mu n for this case particular, but in general it is mu. Cox is the capacitance of the oxide layer, so mu is the mobility of carrier electrons for this case. If it is p-type MOSFET, then if the channel is p-type, it should be holes. Cox is the Cox prime is the capacitance of oxide layer, that is silicon dioxide, and W is width of the MOSFET, that is width of the device width, and L is the channel length, already shown you, and VGS you know, VTH you also know. So the how the W can be shown. Suppose it can be shown like this. I can draw over here. This is n plus source and drain. Between them this is the channel. This is the oxide layer, silicon dioxide, and above there the gate terminal is shown. This is source, this is drain. So here the W is, if we consider this as this type of device, a three-dimensional, if we consider its construction as three-dimensional one, then W is nothing but this one is W. That means the depth, we can say the depth or the width of the device is W. So this is W. It is from the dimensions of the MOSFET. So that W is this one. So it is expressed over this one. So this W and L are the dimensions. This L is the length of the channel and W is the MOSFET dimension, that is the depth of the MOSFET or the width of the MOSFET. So this is the equation, general equation of finding or expressing the drain current in case of without CLM. Now let us find what is the drain current equation considering CLM. Now considering CLM, with CLM, the drain current equation should be like this. We have seen that L is the original length without CLM of the channel, and L dashed is the L prime is the length of the channel after the concept of CLM has been applied with the application of additional voltage delta V between drain to source terminal. The length, suppose it is reduced to a new value, length of the channel to L dashed. So L dashed can be written as, or L prime can be written as L minus delta L. We have seen this. Now let us take L common from here and write it like this. Now you can see that this value delta L minus L, this is called normalized value of channel length. This is called normalized channel length. This is normalized value of channel length. So now we have seen that this delta L by L, the change in channel length per unit length, is nothing but this change is proportional to VDS. That means proportional to delta V, and delta V is a part of VDS. So actually it is the it is proportional to the voltage between the drain and source. Now since this proportion, it is a proportional value, so we can write this as delta L by L is equal to, therefore delta L by L equal to lambda VDS, where lambda is a proportionality constant. And since delta L by L is a dimensionless value, so we can say that if VDS is having unit volt, then lambda is having unit volt inverse, so that if it is having volt as unit volt, then lambda is volt inverse. So as a result, volt inverse into volt is dimensionless. Okay. So now if we substitute this delta L by L equal to lambda VDS over here, so we can write this equation as L prime is equal to L into 1 minus lambda VDS. So with CLM, my new value of ID is ID prime, that is equal to mu COX prime W by L prime VGS minus VTH whole square divided by 2. Okay. Now let us substitute L prime equal to how much? This value, this equation. So put this L prime from here into here. So my ID prime will be mu COX prime W by L into, in the denominator we can write it as like this, 1 minus lambda VDS to the power minus 1 VGS minus VTH whole square divided by 2. We can write like this. Okay. So now therefore ID prime is equal to, we can rearrange this equation, mu COX prime W by L VGS minus VTH whole square divided by 2 into 1 minus lambda VDS to the power minus 1. Now what is this? This is nothing but ID. Therefore ID prime is equal to ID into 1 minus lambda VDS to the power minus 1. Now if lambda VDS is far less than 1, we can approximately write ID prime equal to ID approximately equal to ID into 1 plus lambda VDS. So from this equation we can say, with the help of this part channel length modulation, this lambda VDS, the original current ID is giving us new current ID prime. So this is the way we can explain the channel length modulation in a MOSFET in terms of its current conduction in the form of ID, drain current. Thank you.